Okay, today we talk about section 6.2. This is where we talk about the graphs of the other trig functions. Okay, let's remind us what our basic sine and cosine graph is. Okay. So when we're graphing f of x is equal to the sine of x, or t, or whatever variable you want to use. Okay. One cycle of that, the period is 2 pi. So to do this, I pick a certain amount on my axes and I mark that off as 2 pi. That is, I will complete one cycle in this. Then there are 4 main parts, so I need half of 2 pi, which is pi, half of that, which is pi over 2, and the other half we can count out. Pi over 2, 2 pi's over 2, this is 3 pi's over 2. Now the amplitude of sine is 1, which means I need to go from positive 1 to negative 1. Now the sine starts at 0, ends at 0, and the middle is 0. Now halfway in between here, we peak at 1, and halfway in between here, there's a valley at negative 1. And then we can connect the dots that the sine increases from 0 to pi over 2, increases positively, then it decreases down to 0 until it gets to pi. Between pi and 3 pi over 2, it becomes more and more negative till we get to negative 1. And then between 3 pi over 2 and 2 pi, it becomes less and less negative until it gets to 0. Okay. So that is one cycle of the sine function. Now we can ask ourselves some questions. Okay. Let's look at the limit as x approaches pi from the right. Okay. So now here is pi. I want to be to the right of that. Right? And what's happening to the function? Well, if we just come, when we're looking at limits, let's just stay in this little area. Okay? As we approach, as we go from 3 pi over 2 to just pi, okay, so as we're approaching this direction, the function values are decreasing until they reach 0. Okay? So the function values are decreasing until they reach 0 as we approach from the right-hand side. So the limit of our sine function as it approaches pi from the right is 0. Now, let's look at the limit as we approach pi from the left. Right? So again, we'll just look at a small area here. We're going to approach from the left of pi, okay? And then we'll examine what's happening to the function values. Well, those function values are decreasing until 0 as well. Okay? So as I'm headed this way, the function values are decreasing to 0. So the limit as x approaches pi from the left of the sine of x also equals 0. So in this case, we have that the left-hand limit and the right-hand limit agree, and they're both 0. So when the left-hand limit and the right-hand limit agree, we say the limit exists, and we could write that as, then the limit is just x approaches pi. Okay? When there's no positive or negative, we're meaning both limits from the left and right-hand side agree, and the limit as x approaches pi of the sine of 0 is 0. So this is different than having an asymptote, where the left and right-hand limits may not agree. Okay. Now let's look at cosine. its period is again 2 pi. So I've made my axes, and I'm going to pick a specific amount, say here, and I will complete one cycle in this length of time. Okay. Now we have 4 main parts, so I need to subdivide this. Go half first, which is pi, then half of this area, which is pi over 2. We also need half of this area, and we can count that out. Pi over 2, 2 pi's over 2, 3 pi's over 2. Now the cosine also has an amplitude of 1, which means I need a positive 1 and a negative 1 down here. Now cosine starts at 0 and ends at 0. Or I'm sorry, at 1. Positive 1. Okay. And then halfway in between it valleys at negative 1. And then halfway in between those, we're at 0. And now we can connect the dots. As we go from 0 to 2 pi, that in the first quadrant, the cosine decreases from a positive 1 until 0. In between pi over 2 to pi, the cosine becomes negative and goes more and more negative until it reaches negative 1. Now in the third quadrant here, between pi and 3 pi over 2, it's negative, but it's becoming less and less negative until it's at 0. And then in the fourth quadrant, cosine is again positive, and it becomes more and more positive until it reaches its max of 1. Now let's ask ourselves the same questions about the limit. Okay. Let's look at the left-hand limit. Okay, so the limit is x approaches pi from the left, okay, the cosine of x. Right. So here's pi. I want to be to the left of it, so let's just look in this small area here. I'm going to approach from the left. Okay, so here's pi, I'm to the left, and now I'm approaching it. Okay. Now as we do that, as I'm approaching from the left, we can look at the function values, and the function values are decreasing until they get to 1. Okay, so as we go this way, the function values are decreasing to 1. So we can say the limit as x approaches pi from the left of the cosine is negative 1. We could look at the limit, the right-hand limit as x approaches pi of the cosine of x. Okay. So here's pi. I want to be to the right of it and approach. Okay. So I'm going to be approaching this way. And what happens as I do that? Well, as I do that, the function values are decreasing again to negative 1. So in this case, we see that we have the same scenario, that the left-hand limit and the right-hand limit are the same, that is, we say they agree, and therefore we can talk about now the total limit, that is, the limit as x approaches pi of the cosine of x is equal to negative 1. Okay. All right. Now let's build upon this and look at our other functions. So let's do secant, since we just did cosine. Alright, so if we have to graph f of x is equal to the secant of x, let's remember that's the same thing as 1 over the cosine of x. Okay. Now when we see it like this, you can have parentheses, it doesn't matter. I could not have parentheses there as well, it's fine. So when we start thinking about what it is about the secant graph, we're going to have to remember this, since it really is 1 over the cosine. We have to remember then that the cosine of x cannot equal 0, because when we do, then secant of x will be undefined. Okay. So I think secant and cosecant, once you see this, will be the easiest graphs for us to relate to. Now this time, let's draw it. Let's put our axes, the origin and the center of the paper. We're going to do that because I'd like to look at 2 cycles. So let's call this out here 2 pi, and then this half pi, and this half pi over 2, and this one we can count out to be 3 pi over 2. And we'll do the same in the negative direction. So if this is negative 2 pi, then half of that's negative pi, half of that's negative pi over 2, and this half is negative 3 pi over 2. Now the way we're going to do this is that first we're going to graph the cosine. So let's put in our 1 and negative 1. And the reason why we're going to do this is because secant really is just the reciprocal of cosine. So let's use cosine as a guide. Okay. Now remember, in cosine, it starts at 1, it ends at 1, halfway in between we're at negative 1, and halfway in between that we're at 0. And since I'm just using this as a guide, I want to just dash this in, because it's not part of the actual graph of secant that we're about, when we're finished, that we will graph. Okay. Now let's put another cycle of cosine in. If we went in the opposite direction, then it would, at negative 2 pi, it would also be at 1. At negative pi, it would also be at negative 1. Let's see, it would be positive 1 and be at negative 1. And then again, halfway in between would still be at 0. Okay, so here's me putting in the cosine direction, cosine in the opposite, in the negative directions. Okay, so this is cosine. This is cosine on 2 pi, negative 2 pi is where I start. I'm including that, and I'm finishing at 2 pi. Okay, so you'll see this on your worksheet. So this is what I mean. 2 full cycles, one in the positive direction and one in the negative direction. Now, let's take into account for secant that if the cosine goes to 0, then this function is undefined. Well, from the graph I've just made, I can see exactly where the cosine is 0. The cosine of 0 is 0 at 3 pi over 2, at pi over 2, at negative pi over 2, and at 3 pi over 2. Now, when a function goes undefined, it's going to lead to an asymptote. So let's put in asymptotes there. Let's see, also crosses the x-axis here, meaning that the cosine is 0. Okay. So now I'm done with the prep work, okay? And now we're prepared to actually graph the secants, okay? So it turns out what happens then is that these peaks and these valleys, the cosine and the secant actually agree. So these peaks and valleys are actually part of the secant graph. So I'll fill those in black. Okay. Now if it's the opposite, if cosine is going down, like for example it's going here, the reciprocal function has to go up, and it will go asymptotically close to the asymptote and take off towards infinity. So the same on this side, if it's pulling down here, cosine, then the secant is pulling upwards and taking off to infinity. Similarly over here, we'll have this. And here we'll have this. For the graph of secant. Okay. Now we didn't graph all of these. But beyond 2 pi, it's doing the same thing. Okay. And here as well, it's taking off. And if we had room, we'd see that it was taking off this direction as well. Okay, so that is the graph of the secant. But we have some important questions to answer about this. So, for example, we always want to know about domain. Well, now we don't have a domain that's all real numbers because we have these asymptotes to deal with. Okay. So we know this, but there's an infinite amount of these asymptotes. There's some below negative 3 pi over 2, okay, and negative pi over 2, and then there's the positive pi over 2 asymptote, and there's the positive 3 pi over 2 asymptote, etc., etc. We know that these are the restrictions where those domains come in. Okay? So what are we going to do? We can't just leave it like this. Okay? We need to really write this in a much more succinct way. Okay? So we're going to say that the domain is the set of all x such that x cannot equal something. And let's see if we can't write this in a better way. So the way I like to do it is I always just pick the first positive asymptote. X cannot equal pi over 2. And then I want to examine how far it is to the next asymptote. Okay. Well, if this asymptote is 3 pi over 2 and this asymptote is pi over 2, the distance between those is simply 2 pi over 2, which is just pi. We could look here as well. Let's take pi over 2, the larger one, and subtract the opposite one, negative pi over 2. And this becomes an addition, pi over 2 plus pi over 2. It's 2 pi's over 2, which is just pi. Okay. So in either direction, and you'll find that with all of these, that they're evenly spaced. Okay. So how I use that then in here is that, sure, my first one's at pi over 2, but then there's going to be, the distance to the next one is pi. Okay. The distance to the one over here would be 1 pi, 2 pi. Okay. Just like the distance here is 1 pi, 2 pi. The next one will be 3 pi distances away. Okay. So what we're going to do is we're going to say this is a multiple of k, pi, and then we just have to add where k is an integer. If k is positive, we'll be able to continue going in the positive direction. If k is, say, negative 3, we'd get pi over 2 minus 3 pi, and we'd be headed in the negative direction. So the domain of secant is this. Okay? You take your first asymptote, look at the distance, and determine the multiple. So that's a much more succinct way of saying this. Now let's consider the range of secant. Now remember, secant is just in the black. Okay? So these arrows indicate that it goes down to infinity, specifically negative infinity. Okay? And then it will continue all the way up until this point. And this point is negative 1, and it's included. Now in between here, we just have our graph of cosine, and that's not part of the secant graph. The secant graph doesn't again pick up until we get to 1, and then it continues from 1 to positive infinity. Okay. So the range then is union with 1 to positive infinity. Okay. This is the range for secant. Then given that this is a cyclic graph or a periodic graph, we would like to know what the period is specifically. Okay. So a period does not just occur in between asymptotes. It's where the graph starts to repeat itself. So here I have one, it kind of looks like a parabola, it's not, but looks like there. Then we skip, and then we start down here. It isn't until we get to this point where the graph starts repeating. And if we could see the graph on this side, then it would come over here. So the distance between here is 1 pi, 2 pi's. So even though there's an asymptote in the middle of it, the period before the graph starts repeating is 2 pi away. From here to here, the graph would be at the same point. It is 2 pi distances away. Okay. So we could ask ourselves some questions here too. Let's talk about the limit then. Let's talk about the limit of pi as well. So we could look at the limit as x approaches pi from the left of the secant. So okay, here's pi. I want to approach from the left-hand side. Okay, so start at your asymptote or someplace that's close like that. Okay. So as I approach from the left-hand side of pi, okay, so as I'm going this way from the asymptote in, what's happening to the function values? Well, the function values are increasing. They're negative, and they increase to -1. They'll stop there. So the limit, as x approaches pi from the left, is -1 for the secant. Okay. And we could also look at the limit as x approaches pi from the right-hand side of the secant. So if we're going to approach from the right-hand side, let's start at the asymptote, be to the right of pi, and move in. As I do that, the function values are negative, but they're decreasing until this point of -1. So again, we have the scenario where the left and right-hand limits agree, so we could then say that the limit as x approaches pi of the secant is equal to -1. That is, the left and right-hand limits agree. Let's try and solve this. Let's find out where f of x is equal to 1. Okay. That is, we are trying to solve where is it that the secant of x equals 1. Okay. Well, we can do that graphically. I mean, we could reason it out through the unit circle, but we could just do it graphically. Okay. In this case, I could draw across the line. This is where y equals 1. Okay. And we would see that we have 1 intersection point, 2 intersection points, and 3 intersection points. Okay. Now notice that we're solving then is we're solving this on a restricted interval because there's actually a multitude of these. We are just answering this on -2 pi to 2 pi included. So from here, with these intersection points, we can see then that x must be equal to, well, here, -2 pi, here is 0, and here is +2 pi. So solving graphically, if you know your graphs, is very, very helpful. Okay, now let's do, so that's secant, let's do cosecant. And remember that cosecant is 1 over the sine. Okay. So if the sine of x equals 0, we can't have that because then cosecant is undefined. Okay, so again, since this is the reciprocal of sine, let's draw sine again. And we'll do 2 cycles just as we did last time. One in the positive direction, so I'll pick some value out to here, and then half of that, and then half of that. And this one's 3 pi over 2. Okay. And then one in the negative direction, so this is -2 pi. Half of that's -pi. Half of that's -pi over 2. half of that's negative 3 pi over 2. And then we'll come up here for 1, and down here for negative 1. Okay, so sine, let's put our guide in for that. Sine starts at 0, ends at 0, halfway in between is 0, halfway in between it peaks at 1, halfway in between valleys at negative 1. And then I'll just dash this in because I'm going to use it as a guide for cosecant. It's not really part of the graph. Then we'll do that again in the opposite direction, so it'll be 0 halfway and 0 all the way. Now it has to do the same thing, so this is where it will peak, and this is where it will valley. You can also see the even and odd properties here. The fact that sine is odd means that if this is f of the angle is positive, f of the negative angle is the opposite. Okay. So if you were to fold it over, well, you'd have to do 2 folds. It would lay on top of each other. Okay. All right, so this is our guide. This is the sine of x. Now we know if the sine of x ever equals 0, cosecant is going to be undefined. So any place the sine of x equals 0, that is where it crosses the x-axis, we'll put in the asymptotes. Okay, and now we're prepped and ready to draw cosecant. Okay, just like with secant, the peaks and the valleys are included, so I can put those in with my black pen. Okay. And now it'll do the opposite. So if this is pulling down towards the x-axis, it's going up towards infinity here and infinity here. Here down towards negative infinity. Should probably extend these asymptotes. And down towards negative infinity. Then up, and down, and down. Okay. And this is 2 cycles of the cosecant graph. So here's 1 cycle, then it comes down here. Then it picks back up and starts repeating itself over here. Okay. So in this way, the period is still the same. The period is 2 pi. It doesn't matter that the period includes an asymptote. Right. Now let's ask ourselves about domain. Okay. So there's an infinite amount of these asymptotes, and I don't want to try and list them all because I can't. So let's use our set notation. It's the set of all x, and then we will determine what we're going to exclude. Okay. So if we take our first positive asymptote, that's pi. Okay. Now let's figure out how far it is to the next one. Well, if this one's at pi and the next one's at 2 pi, the distance in between here is pi. And clearly the distance in this direction is pi. So it's a multiple of pi units away. So in this case, I could write plus k pi, but why don't I just put k in like that? Okay. We do have to make a note, though, that k is an integer. Okay. Now we also have the range. So we have this problem that we had before, so there's actually, it skips in between here. So the range starts at negative infinity and goes all the way up to negative 1, and it does include negative 1. Okay. And then it does nothing in between here. This is where the sine lives. So it doesn't start again till 1, and then it goes up to infinity. So this is 1 that's included and goes to infinity. Okay, so this is the graph of cosecant. And we could ask ourselves some solving problems. What if I wanted to know where f of x is equal to 0 on 0 to 2, not 0 to 2 pi, negative 2 pi to 2 pi? That is, we're asking where is it that the cosecant of x equals 0 on this interval? Well, to do that, I can just look up here. Okay. So let me draw in the line y equals 0, and this is the line y equals 0. And now I'm going to look for any intersection points with the cosecant graph. Okay. Well, there is no intersection points with the cosecant graph. Okay. This line is specifically on the interval where the graph doesn't exist. You can see 0 is not included for the range. Okay. So this is no solution. The cosecant will never equal 0. So I don't think the graphs of the secant and cosecant are too hard. We just have to remember to use our base function, put in our asymptotes, and then draw otherwise. All right. Now let's think about the tangent. The tangent takes a little bit more. But the tangent could be our most useful one. So let's do the same thing that we've done. Let's look in positive 1 cycle, so 0, let's see, 0 to 2 pi, then we wanted pi over 2, and 3 pi is over 2. And we may as well do that in the negative direction as well. So we go to negative 2 pi, 0, negative pi, negative 3 pi over 2, and negative pi over 2. Now remember, the sine of tangent of x is the sine of x over the cosine of x. And our ordered pair here, when x is 0, that's 1 comma 0. This is 0 comma 1. This is negative 1 comma 0. This is 0 comma negative 1. And then we're back at 0, 1 comma 0. So when we do this, remember this is our cosine and this is our sine, we get 0 over 1, which is equal to 0. Now for the tangent, we'd get 1 over 0, and this is undefined. At pi, we get 0 over negative 1, which is 0. At 3 pi over 2, we get negative 1 over 0, which is undefined. And at 2 pi, we go back to 0 over 1, which is 0. So we haven't gotten a lot of information here. Well, this also has to be 0. So if we work in the negative direction, now negative 2 pi is down here. Remember, this is the point 0 comma negative 1. So the tangent here is negative 1 over 0, which is undefined. Okay. At negative pi, we have negative 1, 0. So we get 0 over negative 1, which is 0. This is negative 3 pi over 2, so this is 0 comma 1, which we get 1 over 0, which is undefined. Okay. And at negative 2 pi, we're at 1 comma 0, so that's 0 over 1, which is 0. And from 0 we get 0. Okay. So that was not really helpful for us. Okay, but we can put it in. Right, let's try and draw what we have. See at least what we have so far. Since we're going to 2 pi, we'll go up some direction here, 2 pi, then half of that's pi, half of that's pi over 2, half of that's 3 pi over 2. Down here is negative 2 pi, negative pi, negative pi over 2, and negative 3 pi over 2. From our list, then, we can see in the positive direction, at 0, we get the point 0. At pi over 2, it's undefined, so we need to put in an asymptote. At pi, it's 0. At 3 pi over 2, it again is undefined. And at 2 pi, we get 0. In the opposite direction, at 0, we have 0. At negative 2 pi, we have 0. At negative 3 pi over 2, we have an asymptote. At negative pi, we were back at 0. And again, we have this asymptote at negative 2 pi, or negative pi over 2. Okay. So far, that's what we have for the tangent graph. So let's just consider what's happening here in the first quadrant, okay? So the angles that are in the first quadrant is 0, but we already know that. We have pi over 6, pi over 4, and pi over 3. Okay. Remembering the coordinates here are square roots of 3 over 2, comma 1/2, root 2 over 2, root 2 over 2. And down here we have 1/2 square roots of 3 over 2. Okay. Alright, so the tangent has to be the sine over the cosine. So it's 1/2 divided by square roots of 3 over 2, which is 1/2 inverting and multiplying 2 over the square root of 3. And now these 2's cancel, so we get 1 over the square root of 3. And if we rationalize this, we get square roots of 3 over 3. Okay. So this is the tangent there. Now, here we have square roots of 2 over 2 divided by square roots of 2 over 2. Well, anything over itself is just 1. Here we'll have square roots of 3 over 2 divided by 1/2, which is square roots of 3 divided by 2. Now dividing fractions means you invert and multiply. Those 2's will cancel, and we'll just be left with square root of 3. So now we have to figure out how to use these. I hope we can agree about this, that square roots of 3 being divided by 3 is less than square roots of 3 being divided into one part. If you break something into 3 parts, it's got to be smaller than breaking it into one part. Okay. Now the question is, how does 1 fit in here? Okay. Well, let's look at the number line. Okay. So here I have 1, 2, 3, 4, 9. Okay. This is how a number line would go. Okay. So if this is true, then I hope you also believe that the square roots of all of these are true. Okay. That is, the square root of 2 must be greater than the square root of 1. Okay. So the square root of 1 is 1, the square root of 4 is 2. Now here the square root of 3 is 9. Okay. In here, we have the square root of 3. So the square root of 3 is greater than 1, but less than 2. So from here, we can see that we can line these up, that the square root of 3 over 3 is less than this one, and the square root of 3 over 1, which is just the square root of 3, is greater than 1. Okay. So now why is that helpful for us? Well, let's put it on our y-axis so we can see this happen. So if we call this 1, then this is square roots of 3, and down here is square roots of 3 over 3. Okay? So at pi over 4, the tangent has a graph of 1. Okay? And smaller at pi over 6, it's over here at square root 3 over 3, and at pi over 3, it's up here. So what this means then is that this graph is taking off and taking off towards infinity. Okay. Now the same thing's going to happen in the opposite direction. At negative pi over 6, negative pi over 4, and negative pi over 3, this graph is going to be taking off. Okay, down here's negative 1. Should be a little bit more curved. Okay. And it turns out that this is one cycle. Okay. So the difference here now is that the period just goes from here's pi over 2, here's another pi over 2. The period is just pi. Okay. So we can draw in more cycles of the graph, like so. It will just keep repeating itself because it's cyclic. So this is the tangent. Its period is pi, okay, because the distance between any two points that are the same is just pi. Let's look at the domain. So again, we have this problem of removing asymptotes. So we're going to write this as the set of all x such that x cannot equal, and I just pull the first positive one, which is pi over 2. And then how far is it to the next one? Well, the distance between pi over 2 and 3 pi's over 2 is just pi. And the same in the opposite direction because it's cyclic. Okay? So what then we can add then is any multiple of pi, and this is how we can write the domain. Okay, now the range, on the other hand, is very nice. It's just all real numbers. It's one of the reasons why tangent might be one of the most useful functions that we have. Okay, so that's the range. We've determined the period. And now, let's say we want to answer that question again about being equal to 0. Sure. Okay, so if I put that through, this is the line y equals 0, we can see there's 1, 2, 3, 4, 5 intersection points here. So if we have to solve f of x equaling 0 on negative 2 pi to 2 pi, okay, it's a good thing we restricted these because there's an infinite amount in both directions. Then we can see that x is equal to negative 2 pi, negative pi, 0, pi, and 2 pi. And we could ask ourselves limit questions about this. For example, the limit from the left as we go to the angle 0. As we approach from the left, the function increases to 0. The limit as we come from the right, the function's decreasing to 0. Therefore, the limit as x approaches 0 of the tangent is 0. Okay, so now what we have is that, let's do the cotangent. And this is just the reciprocal of tangent. Okay. because remember this is now cosine over sine. Okay, so we're going to have to worry about where sine goes to 0. Well, we know where sine goes to 0. We've done this a couple of times now. So if we draw this in, here's 2 pi, here's pi, here's pi over 2, here's 3 pi over 2. Then we'll do it in the negative direction. Okay. So remember, if we were drawing the sine, it would start, middle, and end at 0. So that's where our asymptotes will go in. And then it's going to look exactly like the tangent. In the middle, everything is equal to 0. So in the middle of the asymptotes, now these are not the same values as the tangent, but in the middle of the asymptotes, these are equal to 0. And where tangent took off this way, it actually is going to take off in this direction and be the flip. And you can verify this by plotting the angle points. Okay, so this is cotangent, and we've actually done 4 cycles of it. Its period is just like tangent. Its period is simply pi. Now the domain, again we have to deal with these asymptotes, so let's just do it in set notation. It's a set of all x such that x cannot equal. Okay, so the first one's pi. And the distance to the one after that is also pi units away, and so this is also pi units away. So in this case, we could just write k pi, where k is an integer. The range is also all real numbers. And now let's solve f of x being equal to positive 1, okay, on negative 2 pi to 2 pi. Okay. So that is, we're trying to solve where is it the cotangent of x equals 1. Okay. Well, somewhere in here is 1. Okay. So as I draw this line in, this is the line y is equal to 1, I have 1, 2, 3, 4 answers. So we know the first one. In the first quadrant, the cotangent will be equal to 1 at pi over 4. In the third quadrant, this happens at 5 pi's over 4. Now notice this is a cyclic function, so the distance between here is pi. So pi over 4 plus 4 pi's over 4 is 5 pi's over 4. Okay? So if you don't want to think about the negative directions, what we could do is we know the distance from here to here also must be pi. So I could take pi over 4 and subtract 4 pi's over 4, which is just subtracting pi. And now this is negative 3 pi's over 4. Which would force it to be negative 7 pi's over 4. Okay. Negative 3 pi over 4, subtracting another 4 pi over 4, is negative 7 pi over 4. So we get these 4 answers. X is equal to negative 7 pi over 4, negative 3 pi over 4, pi over 4, and 5 pi over 4. Okay, so that is section 6.2. It is imperative that you know these graphs and then to think about how limits are affecting them. Okay. I ask you that on the worksheet. And then, it's imperative that you understand how to solve graphically with these and solidify your understanding of the unit circle and how that translates, how the unit circle translates to these graphs. Okay. Email me if you have any questions.